I'm trying to minimize your window, actually. Okay, so thank you very much. My name is Louie Grasso, and I'm going to be talking about a dust event that occurred 16-17 February 2020 in the Eastern Atlantic. Here's listed all my co-authors, and an abstract, I'm not going to read it, that's included for completeness. And so I'll just get right to this here. So this is a GO 16 ABI true color image. This is at 18Z on the 16th. And here you can see the ocean is blue, but we have a lot of aerosol, all this like yellowish brown in through here, and also down on the southern part of the domain here, a lot of aerosol. Calypso, this is the ground track for Calypso, went southeast to northwest, and it moved right through these two dust regions here. The vertical feature map from the Calliope instrument is located down in the lower left of the figure. Moving left to right is going south to north. So I arbitrarily just intersected around 15 degrees north. It's about right in through here. Anything to the north I refer to as the northern dust region, and down here is the southern dust region. And what we can see is there's more yellow in the northern dust region, which turns out to be dust. And there's more mixture of yellow and brown, which turns out to be polluted dust. And so the question is, you know, what is there a viable source of pollution down in southern Africa? Here is the VIIRS active fire map for the previous day. And this is all these dots here are indicating active burning the previous day. So you have previous day's burning, you have easterly winds, transports that smoke out into the Eastern Atlantic, precisely right down in here where we have this aerosol. So this is actually a mixture of smoke and dust. Okay. So what I'm doing is I'm just having an over here on the northern dust region and a dashed horizontal for the southern dust region with some letters here to demark features that you can't see here yet. I'm going to show the split window difference in a second. But here I have a red oval which highlights sort of thicker optical dust. And then here you can see a little more blue, so it's a little thinner. I put a dash line here to indicate the dust appears a little thicker to the northeast, a little thinner to the southwest. All right, so what I'm going to do is show the split window difference for the same time, 18Z. And what you can see here is in general, there's more negative values here. These are -1, -2, and then positive values, the green here. So it turns out Shiwei's presentation on his page 10, figure A, lower left, the green contour, shows very nicely why the split window difference works here, where the brightness temperatures at 10 microns are cooler than actually 12 microns. And so you get a negative dust signal when you do brightness temperatures of 10 microns minus 12, or micrometers actually. All right, so now to the right of the letter B, you see some positive values here, these oranges to the right here, and down in this region. Now we'll go back. And that is actually highlighting some thin cirrus in these regions. And then in the region dominated by C, more a homogeneous orange color, and that turns out to be, appears clear sky here, but that is actually water vapor. All right, so the question is, why is it that the northern dust region, you see a dust signal with negative values of the brightness temperature difference in through here, but yet we can clearly see there's dust in the Calliope instrument in the vertical feature map indicated a mixture of dust and smoke, but yet we don't have a dust signal down in the southern dust region. This is the EU-METSAT dust product, and we use that recipe to include the ABI channels. And so in that recipe, pink indicates dust that you can see here, even the optically thicker dust in this region. But there's this boundary red in through here. When you go to the south, you see more blues. Okay, so here now is another instrument. This is VIIRS, and we can see at 1510, so a couple hours earlier, we can clearly see the dust in through here in the eastern Atlantic, and then the other region down here and called the southern dust region. The split window difference is using the same color table I showed before. However, because the central wavelengths for VIIRS and the bandwidths for VIIRS are slightly different than ABI, you get slightly different values here. However, you still see negative values here, which is indicating dust, and there's this boundary and you start seeing more green. In other words, you're losing the dust signal down in the southern region. Here is ABI brightness temperatures at 7.34, the low-level water vapor. And the key takeaway here is the brightness temperatures are -2 Celsius, and they decrease about 17 down to -19 Celsius, moving off to the northeast. Similarly, moving off to the southeast, we have about a 16°C drop. Coincident with this warm brightness temperatures is drier air. This is the total precipitable water from GFS, and we have 12.7 millimeters, 19, and then going to the south, the values increase rapidly to 50 millimeters. So this is kind of giving you a hint that there is a different atmosphere as far as water vapor in the southern dust region compared to the north. So what I want to show is that the actual air temperatures cannot account for that large temperature, the brightness temperature decrease of about -15, -16. So here in this solid contour is 700 millibar temperatures, and they decrease from 10 to about 6. So that's only 4. And when you head off to the southeast, you go from 10, 8 back to 10. So that's like 2. And at 500 millibars, that's the yellow here, we go from -8 to -10, that's only 2. And then -6 to -4, that's only 2. So the air temperatures cannot explain the what we're seeing here for the brightness temperature decreases. All right, so now here we're just superimposing the total precipitable water on the geocolor at 18Z. And what we see here is in the northern dust region, the dust is associated with much lower values or a drier atmosphere. And in the southern dust region, we have a much moister atmosphere with higher TPWs. All right, so now this is same as the last figure, only what I'm doing is I'm superimposing the TPW values on top of the split window difference. So the blues and the little pinks here are slightly negative, and that's a dust signal. Then we have a boundary here where we get into all the greens. The green is a positive value. Positive value for the split window difference is actually a water vapor signal, and which is supported by the increases of the TPW from 19 to 38 to 50 millimeters in through here. So now we have at a later time at 03Z, we have the advective precipitable water, which is a microwave product. And so here, this is dry air and then moisture air moving to the south. And this is for the surface to the 850 millibar layer. Similarly, for the 7 to 500 millibar layer, we have dry air to the north associated with the northern dust region and moist air to the south. So we're having different sensors here kind of telling the same story, that we have dry air to the north, moist air to the south. And this is simply going along with the same time period, 03Z. We still see a dust signal to the north, and we have a water vapor signal to the south. So here now is NewCaps. This is TPW derived from the NewCap system, and it's the same scenario where we have lower TPWs here of 12 to 14 millimeters, and values increase considerably to this, going to the south to about 36 millimeters in the eastern Atlantic. Here are these dots, green dots here, show where retrieved soundings can be acquired. So we actually looked at quite a few retrieved soundings in through here, and they all look very similar. So I'll show one representative one at this point 1, And we looked at several down here in the south. I'll show a representative at location 2. So in location 1, what we see is a considerable temperature in red dew point spread several tens of degrees in the northern dust region. But sounding 2 in the southern dust region, we have a moister atmosphere. Also, since we know that in the northern dust region, the blue here corresponds to dust, what I did was I made a time series from 1830, and I went every hour and a half to show that this dust can in fact be tracked in time even when the sun has set. So one of the key features here that is sort of a sharp contrast or a love-hate relationship between water vapor and dust. People who are interested in water vapor retrievals will say the dust is interfering with water vapor retrievals. However, the dust folks will say water vapor is interfering with dust. So this is a clear example where we have water vapor is actually masking dust detection in the southern dust region. And then all these figures are contained in a publication. Here's the complete reference. And then finally, that's all I have. Thank you.
Oh, thank you, Louie. But you have 10 minutes left. Is it okay?
Yeah.
Thank you. Does anyone have questions or comments? I have a question, Louie. The dust detection using channel differences is very convenient, but I'm afraid that sometimes the dust detection using channel differences depends on the time, I mean, in daytime or nighttime, isn't it? Right?
No, that's one of the benefits actually of using the split window, because these are infrared channels, and so there is no solar component. The solar component is very important for what I had showed earlier. I'll bring it back up. We'll go back up here. For example, this image here, where we can actually see the dust. However, I'm going to kind of move you over here. On the right side of the image, you can see the day-night terminator is located right here. So once nighttime occurs, this whole scene gets dark, and you're not going to see any dust. However, that is the benefit of the IR technique, is at these time here, 20, 21, 23, there's no sun, but yet you can still identify and monitor the movement of the dust.
Yes, it's very convenient, but my question is, the detection error is different from daytime and nighttime. I mean, for example, in the Gobi Desert, or I often use the channel difference products, but the error is different in the morning or in daytime, night times.
So that's right. The difference between using the split window difference over the ocean and over land is over ocean, you're not going to see a diurnal cycle that you will see over land. Exactly what you're talking about. That's right. You will see a definite diurnal cycle over land. In addition to, over the ocean, you don't have sort of a difference in emissivities between these two infrared bands. You absolutely do have a difference in emissivities over land. So you can have, for example, false signatures dust or things over land simply because of the difference in emissivities. So there's sort of an advantage of using the IR technique over the ocean, where you eliminate a solar cycle and you eliminate sort of the differences in the emissivities, because the ocean's, it's water. But over land, you have a lot of variable surface types. And that's what's happening over, the United States, the Gobi Desert, Africa, and things like that.
Thank you. Any further questions or comments? If there's no other questions, let me move